All right, so we're going to look at lesson 22.3, properties of logarithms. Our learning goals today, we're going to make conjectures about properties of logarithms, write and apply the product property and quotient property of logarithms, and rewrite logarithm expressions by using properties. So to kind of refresh what we know about exponential properties, if we have a to the n power times a to the n power, if our bases are the same, what do we do with our exponents? Add them. So a to the m times a to the n would be a to the m plus n. When we divide and our bases are the same, what do we do with our powers? If I have a to the 5 and a to the third, you subtract them, so I cancel out what they have in common. And so 5 minus 3 is 2. So a to the m minus n, we subtract them. And then if I have a power to a power, so a to the m to the n power, what do I do with the exponents? Multiply them. All right, so we're going to be using common log, so it's going to be the button on your calculator. So if we have, if you on your calculator, if you do log of 1, what do we get? You get 0. Log of 2. And 3. And then log of 3.
0.47.
What is it?
0.47.
0.47.
0.60. 0.77. 0.84. You could have done that in 0.9.
0.77.
8.4.
0.9. And then log of 9.
I have one.
Is that a
The next one there.
Log of 9.
Red light key.
Point nine.
Or like one or the other.
All right, so the board is super not aligned.
I remember when this guy used to so mad at Chandler because he could see his writing.
I remember Katrina used to say, I was like, can you just stop doing that? I remember when I knocked on the door.
All right, so let's look to see what's happening. So we've used our calculator to create our table.
Why am I so lower?
Well, we went back. Like our homework was ahead of us.
It's AC up on this. Yeah, these are the days where we're all just gonna sweat.
All right, so log 2 plus 3. So if we add these together, so log 2 plus 3 is
0.39.
One of these days I'm gonna show up in Stato.
no.
0.39.
Just made by the sides. It's not illegal. You won't.
So log 2 plus log 4, so 0.3 plus 0.6. Log 2 plus log 5
Can
is.
you not do that on your calculator or what?
0.43.
You can.
It's not working.
Okay, well there's a certain property, so let's just add them up, and then we'll look at it.
Oh, there you go. That's the
Okay, so 0.3 plus point. I don't know what I have. Is that 7.6?
6.
It's on tall.
6
1.
for what one?
1.
For 5.
1. Still the answer.
0.69 or 5.69. 0.69.
1.
log of 3, so 0.4. Okay, so let's look. So log 2 plus log 3 equals 0.77. What other log has a 0.77? Log of 6, right? Is there a relationship between 2 and 3 to get 6? So log of 2 plus log of 3 equals 0.77. Log of 6 also has 0.77. So what's the relationship between 2 and 3 and 6?
When you add them together,
We get 6. But the numbers 2 and 3, how do they make 6? We multiply them. So we have 2 and 4. So we add those together, that gives us 0.9. So what's the relationship between 2 and 4? When we add the logs together, we get 8. But 2 and 4, how do they relate to 8? We multiply them. So 2 and 5. When we add them together, we get 0.99, which is nearly 1, right? And which is the log of 10. So 2 and 5, how do they relate to 10? Multiply them. When we take log of 3 and add it to itself, we get, I didn't write what that equals. What's 0.47 plus 0.47?
0.95.
0.95. Or 4, which is nearly 0.95, right? So what's 3 and 3? How does that relate to 9? Multiply them, right? So when we add 2 logs together, now these are all have a base of 10, which is your common log. So when we add them together, what are we doing with the results? Like, how does that relate to this number here? What are we doing? How could I combine this? Instead of saying log of 2 plus log of 3, I could say log of 6. And then instead of saying log of 2 plus log of 4, I could say log of 8. And instead of saying log of 2 plus log of 5, I could say log of 10. And instead of saying log of 3 plus log of 3, I could say log of 9. And so it all equals the same stuff. Alright, so what we're doing is we're going to start looking at the properties, and log functions are useful in different manners if you're trying, anything where exponential functions are used. You're going to use log functions to kind of work backwards. If you're trying to figure out exponential functions will tell you how much medicine is in a person's system. Log functions will tell you how much you need to administer to get them cured without ODing them. Yeah, I'm guessing it's not. So if you're going to go into pharmaceutical research, this would be great. You also, so like anything like nuclear research. Finance uses it a lot as well. Finance uses it if you're going to go to any business or banking. Finance uses it so much. That's actually where the letter E came from. It's the finance thing. So, yeah, bankers, right? All right. So, looking at number 4, we want to compare the answers in item 3 to the table of that in item 2. So, letter A is just, what did we find? What's the pattern that we found? So when we're adding 2 different logs that have the same, that are, the same base, so both common logs. So when we're adding those together, what would be, instead of punching in 2 different numbers, how could we only, right, so multiply your results together.
Are you recording?
I am. Alright, so kind of putting it into their letters. So how would I write this? So log of n plus log of n equals log of n. so explain the connection between the property of logarithm stated in item 4 and the corresponding property of exponents in item 1. I forgot what item 1 said. Alright, so how does our log property relate to the exponent property? So which one is it? Is it like? The third one, right? And so we have, or it's kind of like the first one, but working backwards, right? If we add our exponents, if we're multiplying the bases, adding the exponents, but now we're adding our log functions to get to, I guess, similar. So here we're going from adding to multiplication, and here you're going from multiplying to adding your bases. Alright, so let's graph this and see what happens. Keith, are you paying attention? Alright, so looking here, we have log of 2 plus log of x. So the addition property tells us that if we're adding the two bases together, we can combine them and multiply them inside one log. So if that's true, then this should be the same, right? And what do we notice about the two graphs? They're the same, right? All right, so in this one, in number 5, we said it kind of related to that first property, but it was kind of in reverse, where here we're adding, and then our result we multiply when we want to combine them together. So here we have our two separate, we're multiplying the bases, but then we add the exponent. So if we look down at number 9, if this is our exponential property, if we divide the bases, same base, then we subtract the exponents. What do you think? How do you think that's going to relate to the log property? And remember, log functions and exponential functions are inverse, so kind of looking at it in backwards direction. So let's say if I have log of 5 minus log of 1. Instead of having 2, how could I write that as 1 log? How could I combine them? Alright, so let's look at it. Alright, so here with the exponent, with our log functions, if we're adding, then we multiply. So what would be kind of we're going to divide. So we're going to take, we want to combine it as 1. If we're working this backwards, we have our logs we're subtracting. So we combine it into 1. we'll divide them. Does that make sense? Let's look at it. We can look at the table too. So if we do log of 10 minus log of 5. Log of 10 is 1, and then we subtract 5, which is 0.69. This gives us 0.31, right? Right, that's close to log of 2. Well, how can I take 10 and 5? How can I relate them to get 2? Divide. So taking this, I can take my two numbers, divide them, and then log of 10 equals that same thing. We can do the same thing if we do log of 10 divided by log of 10 minus log of 2. I have 1 minus 0.3, which is 0.7, which is nearly log of 5, right? Log of 9 minus log of 3 equals 0.95 minus 0.47, which is 0.48, which kind of the surrounding errors is log of 3, log of 9 divided by 3 equals pretty much the same thing, right? Approximately. I mean, we had rounding. Does that make sense? Subtracting the logs is equal to dividing the numbers inside one log. Is there a better way of? Okay, and we did this. We had log of 10 minus log of 5. Alright, so for fun, let's hold off on that for a second. If we do log of 20 minus log of 4, what do we expect that to be equal to? -0.69.
Must be around the 90.7.
Alright, so we have log of 20 minus log of 4. So to combine these into one log, I'm taking this number and subtracting this, but it's not quite, if we take log of 16, is that the same? No, what do I have to do to these two numbers if I want to combine them? Divide. And then log of 20 over 4, which equals log of 5, and what's log of 5 that we found from our table up top? 0.69. How are we feeling about that? Logarithm, it's the inverse function of exponentials. And so we're looking at properties of them. And all we're doing is as you gain experience working with them, you need to know how to manipulate them to solve them because of your x being in sunny spots. So logarithms are what you use if you need to find out if you have an exponential function and you need to solve for x. This is how you would undo that. Alright, so it says graph it, so we're going to do a visual. And what would we expect the log of x minus log of 2 and log of x divided by 2? What would we expect those two graphs to look like? We would expect them to be the same. And they are. Yep. No, Wednesday. Wednesday. Okay.
Can we forget about homework and just go over the test?
We have time. We can go over. We can look over the test, and that way it will help me with your review, because we still have one other property to look at, which is the power property. Yeah. All right. All right. So your test. Okay. 357 for if you're looking for it. All right. So tell whether or not each table contains data that can be modeled by an exponential function. Provide an equation to show the relationship between x and y for the set of data that are exponential. So kind of look at it, you know, in order for it to be exponential, what should you be doing from to, you know, between all of your y's? If it's exponential,
it has to be the same.
Same change. So are you adding, multiplying, dividing, subtracting? Multiplying, right? Because that's the whole point of exponentials. It's fast multiplying. So you know, look, are you multiplying the same amount each time? If it's yes, then it's exponential. If it's not, then you just write no.
So both the top and the bottom have to be the same amount. Basically,
If you need to. Yep. So I think we did that in the very first. Alright, so we went over that in, I want to say it was 21.1.
Then just put yes.
Right?
You just put yes and then you write the equation if it's yes. If it's no, then you just put no. So here we can do one. All right, so here we have. No, let's see. So here we have our first term, and then each time, what did we multiply by? Well, 1.2, right? So we have. Now there's got to be a table in this lesson. So this is 21.2. All right, here we go. So if I'm looking here, I have 1 to 3. What did we? Because this side we're increasing by 1 each time. So from 1 to 3, what do we multiply by? 3. From 3 to 9? 3. So is this exponential? Yes, because we're multiplying by 3 each time. If it was linear, we'd be adding that same amount. But here we're not adding the same amount. Because here we're adding 2 and then 3 and then more.
Flip the y. So you started out with 81.
Well, then you would be dividing by 3 each time. And so dividing by 3 is the same as multiplying by. Woo!
That's a line.
That is the best line. That's what we're going to run all year. If I divide by 3, it's the same as multiplying by 1/3. Alright, so if I was to make up the equation for this, what's our B value? 3, because that's what we're multiplying by each time. And then A is our starting value. So what do we have as our, what's our starting value is 1. We don't have to write the 1 if we don't want to. 21.2. So 328. And then for this one, here it's times 2, right? And then 8 to 14, is that times 2? So is that one exponential? So number 2, tell whether or not the function is increasing, state increasing or decreasing, and give the domain range and the y-intercept of the function. So this is going back to the transformations. We kind of looking at 21.2 and 21.3. So we looked at increasing or decreasing. So with exponential functions, we have 2 options. You can have growth or decay, right? So if you have growth, you can have increasing growth, and decreasing growth. Increasing growth would be, an example would be an investment. As you save more money, your savings account. Your graph is going to go like this. You're going to add more money, and you have your interest and all of that. Decreasing growth would be when you get further in debt, all right, which is never a good place to be, but your debt would be growing exponentially, increasing. And then you can have increasing and decreasing decay. Decreasing decay would be, like with the nuclear waste, you get less of it each year. And then decreasing decay would be if you have a credit card and you pay half of it off each month. Even if you only pay half of it, you're still always going to have that debt because you're never going to have half of nothing. Because if you get to the point where you're paying pennies on it. So with an increasing or decreasing function, you need to, is it growth, is it decaying, and then is it approaching positive infinity or negative infinity, or is it approaching zero from the positive side or from the negative side? So with decay, in order to have decay, what has to be true about your b? What has to right, between 0 and 1, right? And then for growth, your base is greater than 1. And then to determine if you have positive or negative growth, what determines that? Right, the negative sign in front. So like here, there's a negative. So that one's definitely going to be, in the bottom half of your graph. So that doesn't mean that it's always decay, but it doesn't necessarily mean that it's, going to go to positive infinity. And so the best way to do those would be to, sketch yourself a graph. We had looked at, so what would be an example of a growth function? So y equals, give me an a value, and then give me a b value that would be growth. 4. That's a good one. All right, so we have this value here. So this is our graph. So this is increasing, right? We're going to positive infinity, and we're following our y-axis. I can make that a negative growth by just adding a negative sign in front. And now we're decreasing exponentially down that y-axis. I think I have half of them. I don't remember what I did last week. All right, so if I do, I'm going to use the same a value, and then what would be a b value that would be decay? 1/3. All right, so here, our graph, we're approaching our x-axis, so we're approaching 0. So as all things decay, at some point, it'll get close to 0, but theoretically, you'll always have something left. And in this case, we're going to decrease by 1/3 each time. I can make this so now I have an increasing function, right? Because I am increasing, but I'm never going to get positive because it's the debt is decreasing by 1/3 each time. But we're never going at that rate. We'll never get out of debt. Yeah. So this is decay. So this would be with this graph. If I'm going from left to right, am I increasing or decreasing? I'm increasing this way. And then this one, is this increasing or decreasing? Decreasing. So this would be decay, that's decreasing. And then this orange line, is that one increasing or decreasing? Decreasing. So it would be negative growth. Decreasing. No, I think it just said increasing or decreasing, right?
Are you talking about 2?
Yeah, 2.
So
Alright, so there's your diamond. So this one here, is this increasing or decreasing? Increasing. Alright, so let's look at the last one I just did. So what would be the range for this one? So range is for which letter?
Negative y.
No,
Oh,
it's
it's
zero.
y.
Zero. Is let's make it the negative.
Plus normal.
All right, so domain and range. Domain goes with your x, range goes with your y in alphabetical order. All right, so domain goes with our x. So what are all the x values that can go into our equation? And I heard it. Yep. So we can go there. There's no x value that won't work because we're never going to have anything undefined or imaginary. So our domain would be from negative infinity to positive infinity. What about our range? Our range is looking at our y-axis.
So it's zero.
So 0 to positive infinity. Alrighty. We'll go over the rest of it tomorrow. Your homework. Your homework is page 352. 15 through 18.